Hello, welcome to the fourth lesson of electric circuits and circuit analysis. Today we're going to look at the node voltage method and do various examples. Essentially, the node voltage method is an application of KCL where we substitute the currents for the respective voltages over the nodes. Let us, as usual, begin with a circuit diagram. Okay, wonderful. What we've defined here is a 10 volt 10 volt voltage source, a 1 ohm resistor, a 2 ohm resistor, a 5 ohm resistor, a 10 ohm resistor, and a 2 amp current source. Essentially, what we want to do with node voltage is find out what specific voltages are within nodes in a circuit. We define an essential node as when 3 or more circuit elements connect at a node. So this would be an essential node, this would be an essential node, and this bottom node would also be an essential node. So we define a voltage, V1, and another voltage, V2. Very importantly, and a trick that we often use within circuit analysis is to define a reference ground. A reference ground can be symbolized through this symbol or this symbol. I always prefer this symbol. A reference ground allows us to define an arbitrary point where V is equal to 0. And this really simplifies our equations. The node voltage method often encourages us to create simultaneous equations. So hopefully we're familiar with that. We know that we need one for every defined variable. So let's take this node of V1. What is KCL at that node? Well, we always define with node voltage all the currents leaving the node. This is just standard practice. So we define all the currents leaving the node. So we have I1 plus I2 plus I3 is equal to 0. Now what is I1? I1 is the voltage V1 and the voltage drop from this point to this point. So minus 10 over the resistance. So that is the current I1 flowing from this point to this point. Similarly, we can do with I2. We have I2 is equal to V1 minus V2 over 2 ohms. So this is simply Ohm's law. I is V over R. And we do the same with I3. We have V1 minus 0 over 5 ohms. So this 0 is now our reference ground. Because we've taken this as 0, we can say that the voltage drop from here to here is V1 minus the 0 volts. Let's take all three of these and we add them into this equation. So then we have V1 minus 10 over 1 plus I2, so it's V1 minus V2 over 2 plus V1 over 5 is equal to 0. So this is the first equation, and this is essentially how we do the node voltage method. So let's take V2 this time. We're going to go a bit quicker. As always, I said that we take the current leaving the node. So we have I2, we define this as I3 plus I3 minus 2 equals 0. So as I said, all the currents leaving the node, however, the 2 amps is entering the node. So we add the negative symbol. So I2 we define now as V2 minus V1 over the 2 ohms. So it's the voltage drop over the resistor, V2 minus V1 over the resistance. Similarly, we do with I3, so it's V2 minus 0 over the 10 ohms. And that minus the 2 amps entering the node. So this is our second equation. Note that we have two simultaneous equations and two unknowns. Therefore, we can take one of these variables and make it the subject of one of the equations and sub that into the other, and we can get the value for the other variable. And that is exactly what we're going to do. We take equation 1, which is now V1 minus 10 plus 1 over 5 V1 plus a half V1 minus a half V2 equals 0. So then we sum all of the V1s together and we get 1.7 V1 minus 10 is equal to 0.5 V2. We do the same with equation 2, and we get 0.6 times V2 minus 2 multiplied by 2 is equal to V1. So essentially what we've done is we've taken 0.5 of V2 and 0.1 of V2 here. We've summed them to get 0.6 of V2. Then we have minus 2, and we've taken V1 to the other side of the equation, and we've multiplied that 0.5 over this. So we get V1 is this. And we simplify that one step further. We get V1 is equal to 1.2 times V2 minus 4. Now what we do is we've got this equation. Take this as our third equation. Then we take 3 and we put it into 1. So we have 1.7 multiplied by V1, which is this. So we have 1.2 times V2 minus 4 minus 10 is equal to 0.5 V2. Then we multiply out this bracket, we get 2.04 V2 minus 6.8 minus 10 is equal to 0.5 V2. Last simplification step, we have 1.54 V2 is equal to 16.8, and then we get V2 as 10.9090 recurring. So we simplify it just to 10.909 volts. Then we can accordingly get V1, which we know to be 1.2 times V2 minus 4. So we sub that in. So we have 1.2 times 10.909 minus 4 equals 9.091 volts. And there we go. We have gotten V1 and V2 from using the node voltages in this circuit.